In section 5.3, we're going to talk about conditional probability and independence or independent events. First, you're going to calculate and interpret conditional probabilities. So the probability that one event happens given that another event is already known to have happened is called a conditional probability. Suppose we know that event A has happened, and the probability that event B happens given that A has happened is denoted by probability of A given that B has happened. So this vertical line here is essentially saying probability that A happens given that B already happened, or given that B happened. So that second event behind the vertical line is the condition, part of the conditional probability. Now how you actually calculate these is you take a probability that both events occur and divide it by a probability that the given event occurs. So if you're looking for the probability of A given that B has already occurred, you simply divide these two. The given event, the probability of that happening, is always in the denominator. The numerator will be the probability that both events occur. So A and B divided by the probability of just B. So whatever is given or the condition, that's always going to be in the denominator. If you were to want to write probability of B given that A happens, the only thing that changes here is that the denominator is now probability of A. The numerator is still the probability of both events happening. So whatever the given event or the condition is, that's the probability that goes in the denominator, and then the probability of both or and happening is on top. So let's actually use this on an example. Find the probability of picking a female at random given that they have pierced ears. All right, so it's actually kind of helpful if we just call these things A and B. So let's call A let's call A male, and B is going to be pierced ears. Okay, so the complement of A would be female, and the complement of B is non-pierced ears. So a probability of picking a female at random, so picking a female would be complement of A, given that they have pierced ears, looks like that. So remember the given, the condition, that's always your denominator, probability of B happening. Then you're looking for the probability of complement of A and B happening at the same time. Okay? So what this is going to be is the probability that B is going to happen pierced. You look for the number of pierced people. So pierced ears, yes, it's going to be 103 out of 178, but we don't need to write the denominator in the fraction. And then female and pierced, so female pierced, where they intersect, is 84. So 84 out of 103 is your probability, your conditional probability, or 0.1 or 816 or 81.6%, however you want to state it. Next, find the probability of picking someone with pierced ears given that they are a female. So this may look like the exact same statement, but it is written in the opposite direction. So the probability will be different because it's a different condition. So the condition here is that they are female. So given that they are a complement of A, find the probability of B. Now our denominator is going to change, but our numerator is not. So now we have probability of complement of A. So what's the probability of picking a female? And then on top is going to be probability of complement of A and B happening at the same time. So that number 84 we'll reuse right here. Now down below, what's the probability of getting a complement of A or a female? That's going to be a total of 88 out of 178, or just 88 in this case. 84 divided by 88 is going to be approximately 0.955. So even though we're using the same two events, the condition's in the opposite direction, so you're going to get two different probabilities here. All right, let's look at this problem here. The probability that someone reads the New York Times is 0.25. The probability that somebody reads USA Today is 0.40. The probability that someone reads both is 0.05. What is the probability that a USA Today reader also reads New York Times? Some people, when they read this statement, think immediately, oh, it's 0.05, because you're looking for and, both, right? Well, the way this statement is read, it's read as a condition. So what is the probability that a USA Today reader also reads New York Times? Your condition is you're only looking at USA Today readers. Out of those readers, how many also read the New York Times? So your condition is they read USA Today. You want to find the probability that they also read the New York Times. So on the bottom, probability they are just USA Today readers. And on top, you're going to find the intersection of the two. Remember, the given or the condition is always the denominator here, and then the and, find the probability of both events happening. Okay. USA Today readers, 0.40, that's your probability given to you in the problem right here. Probability they both are read by someone is 0.05. So when you calculate that, you get exactly 0.125 or 1/8 or 12.5%. So be careful when you read statements to make sure that is it a conditional probability or is it an intersection they're referring to. Okay, so we have talked about in previous sections the general addition rule. We also have a general multiplication rule. And it's actually just a rearrangement of the equation we already talked about. So we're going to rearrange the conditional probability formula. You remember that looked like this. Probability of B, given that A happened, is the probability of A and B divided by the probability of A. So here, all you have to do is multiply both sides by probability of A. That cancels. And what this turns into is the general multiplication rule. Probability of A and B, or both events happening, is the probability of A multiplied by the conditional probability of B, given that A has already happened. And this works for conditional probability or independent events as well, and we'll show you how that changes for the independent events, this equation. So an example, tennis great Roger Federer made 63% of his first serves in the 2011 season. When Federer made his first serve, he won 78% of the points. When Federer missed his first serve and had to serve again, he only won 57% of his points. Define event A and B, and then create a tree diagram for the respective probabilities. So we'll make A, the first thing that happens, makes first serve. Then we'll make B, wins point. So that makes the complement of A, misses first serve. And that makes B complement, loses point. And because they give us probabilities for the B or B complement depending on A, this is a conditional probability setting. So, first tree deviation, we have 0.63% of the time he makes first serve. That's event A. And then the complement rule says that if it's 0.6 or 63% of the time he makes it, that means 37% or 0.37 he misses the first serve. That's complement of A. Now from there we have respective probabilities. They give us that when Federer made his first serve, he won 78% of the point. That's this branch here. So 78%, he wins the point. That's B. And so that means that 22% of the time, or 0.22, he loses point after winning or missing, or sorry, making the first serve. He only won 57% of the points after missing the first serve, so 0.57 winning point or wins point. And that means the complement rule states that he actually lost the point 43% of the time. So this is our tree diagram. If you want to define the probability of each branch, you simply multiply the respective probabilities. This is the probability of A happening. This is the probability of B happening, that given that A has already happened. And you notice because these two add up to 100% along with these two, but not these two or these two or these two or these two. It's respective here based on event A happening. These two are based on event A complement happening. So if you want to find the probability of A and B in this case, you're simply going to multiply 0.63 times 0.78. Probability of A and B complement happening is going to be 0.63 times 0.22. Probability of A complement and B happening is 0.57 and we should do 0.37 first and then 0.57 second. And the probability of complement of A and B complement is going to be 0.37 and 0.43. So this is the general multiplication rule in action here. You just multiply the separate branches of the tree diagram. So if you want to find the probability of this event happening, A and B, you do this branch times that branch. You want to find the probability of A and the complement of B, this branch times that branch. Simple multiplication rule. And when you multiply all of these out, you get 0.4914. This should be 0.138, 0.2109, and 0.1591. And these four respective probabilities, when you add them together, you should get a total of 1.000. That's because these are all the possible events that could possibly happen. Nothing else can happen here that's not in the sample space already. So right here, everything that's here is going to, one of these things is going to happen. So if one of these things has to happen, your sum must be 1. There's no missing probability.